So first I'd like to introduce you to what is the familiar, that is Pythagorean triples of the equation a squared plus b squared equals c squared. So an example of this is 3 squared plus 4 squared equals 5 squared. Another one is 7 squared plus 12 squared equals 13 squared. And what you'll notice is that Pythagorean triples are integer solutions to this, and there are many, many integer solutions to this. However, what is probably more unfamiliar is something along the lines of a cubed plus b cubed equals c cubed, or a to the 4 plus b to the 4 equals c to the 4. The reason why that's unfamiliar is because there's no whole integer solutions to that. There's no a, b, and c all integer solution to any of those. And that works for any integer n that is greater than 2. You can't have a to the 5 plus b to the 5 equals c to the 5 either. And the first person to say that there are no integer solutions for any n greater than 2 was Pierre de Fermat. And he was a mathematician who proposed this idea in the 1630s. But he didn't have a proof to prove why. Actually, Fermat came up with lots of theorems. He came up with many, many theorems. But the problem is that he didn't have proofs for all of them. And over the years and centuries, all of them either became proved true or proved false, except for one. And that was this one, which we didn't have a proof for the longest time. And it was therefore known as Fermat's last theorem, because it was the last one to be proved or disproved. And eventually, it was proved and it was solved by Andrew Wiles in the 1990s, a mathematician who dedicated over a decade of his life to this problem. And he came up with a very long proof that is very detailed, using all of mathematics at his side, in order to prove that there is actually no integer solutions for any n greater than 2. However, what you'll notice is that n equals 4 is a particular case, and it was proved a long, long time ago, way before Andrew Wiles. So I'm going to be going ahead and just showing you a proof of that today, even though this more grandiose problem with a more grandiose proof was proved very recently, which I think is a very exciting innovation in mathematics. So first I'm going to be showing you Euclid's formula for Pythagorean triples. And we're just going to end up rewriting a, b, and c in different ways, and you'll see that, and we're going to use it later. So if I have integers a, b, and c, I can plug it into a squared plus b squared equals c squared. Let's say we have a Pythagorean triple solution for this. We can then divide everything by c squared, and we'll go ahead and get this solution. Now, what you'll notice is that if we make a point a over c and b over c, is that a over c and b over c are very obviously on the unit circle. That's because if we square the x term and square the y term, we end up getting 1 as the radius. Let's go ahead and plot it on the unit circle as point P. Let's also go ahead and plot another point on the unit circle and label it Q at 0, -1. This will all come in handy later. Let's also go ahead and draw a line QP from Q to P. And let's label point R as the intersection from QP. Let's define R to have x position k, and its y position is obviously 0, since it is on the x-axis. Let's also go ahead and define point P as x sub 1 and y sub 1. So x sub 1 is just a different way of writing a over c, and y sub 1 is a different way of writing b over c. But it'll be easier to look at when we start doing calculations. So another way of writing QP in point slope form is y equals y sub 1 minus -1 over x sub 1 times x plus -1. We get the -1 as the y-intercept from point Q, and we get the slope by taking y final minus y initial over x final minus x initial. So we have y sub 1 minus negative 1 all over x sub 1 minus 0, which goes ahead and gives us this, because we're going from point P minus point Q. And then if we plug in R, we can go ahead and get this. So I'm plugging in R so that I can go ahead and solve for K. So you see that I have this, and I'm just going to go ahead and solve for K and go down here. And now I get K in terms of x sub 1 and y sub 1. Another important thing to notice is that, well, right here, is that K must be a rational number. What that means is that it must be able to be represented as a fraction with an integer numerator and denominator. And that is also going to be positive since it's on the right side of the y-axis. And it must be rational because A and B are integers, and C is also an integer, and Q has integer points, and it's formed from a straight line between them. And just simple division of x sub 1 and y sub 1, which are all made from integers, just being divided. So K must be rational. Okay, so we have original formula for the equation of the line, and I'm going to go ahead and plug in K. So if we go back here, what we notice is that K is actually the inverse of the slope of the line. So instead of the slope of the line, we can just have 1 over K. And let's go ahead and solve for y and x in terms of K. And there we go. We have y and x in terms of K. But let's go even further as well. Since we know that K is in a rational number, which means it can be a fraction, we can go ahead and put it in terms of n over m, where n over m is just a simplified fraction for whatever K is. So there we go. We replace K with n over m. Let's go and simplify. There we go. So now we have x in terms of n over m and y in terms of n over m. Now here's those two equations again. And we also have y written as b over c and x as a over c. And what you'll notice is that they share a common denominator. So we can just set that to c and set b to the numerator and a to the numerator of x. Now, this is a very easy way to write a, b, and c in a Pythagorean triple as different integers and equations that work for them, because we defined m as an integer and n as an integer. And another thing to note is that n and m, since it's a simplified integer, we defined it as that, they won't share any factors at all, which means that they are co-prime with each other. They don't share any factors in any of these equations. Now let's look at another quick proof for something of what it means to be co-prime. So if we have a squared plus b squared equals c squared, they're all integers again. Let's just go ahead and assume that. But let's also assume that a and b can actually have this number factored out. Let's say it's d. And since it can be factored out, a divided by d must be an integer, and b divided by d must be an integer. Let's set a over d to be alpha and b over d to be beta. So now we get this, where I factored out a into a and d and b into beta and d. Now, let's go ahead and factor out the d from the whole equation. And then we can divide by d squared and go ahead and get this. And we know that alpha squared plus beta squared must be an integer since we said that alpha and beta were integers, which means that c over d squared also has to be an integer. So if we ever have something similar to this, even if we don't have a c over d all of it squared, where c is an integer, we know that the right-hand side of the equation still is an integer. And we can go ahead and see another thing, and that is that c is actually divisible by d in this case. So that means that if a and b are not co-prime in the sense that they have a factor, that C also must have that factor, so it's not co-prime. But if A and B are co-prime, then C has to be co-prime. And actually, if A and B are co-prime, back from up here, whatever it equals must also be co-prime to it, since we start from the right-hand side of the equation. So in a Pythagorean triple, A, B, and C, either A, B, and C are all co-prime, or none of them are. Either they all share a common factor, or none of them do. Let's keep that in mind. So let's actually go to the Pythagorean, let's actually go to Fermat's last theorem again, with a to the 4 plus b to the 4 equals c to the 4. Now, let's assume that there is a solution for this. So if there's a solution for this, we can write this, and then we can just define w as c squared. So rewrite it this way. Now, a thing to note is that we can rewrite it this way as well, as just a squared squared plus b squared squared is w squared. Now, there must be a minimum w. Since there's integer solutions for c, there must be a minimum integer solution for w as well. Let's keep that in mind as we go forward. W is the smallest possible answer of what c squared must be. We're defining it as the minimum. So since we have an a squared here, we can go ahead and set up that Euclid's Pythagorean triple set before, where a squared is now 2pq, b squared p squared minus q, and w is p squared plus q squared. And p and q are all integers. So let's go ahead and keep that in mind. This is just rewriting it a lot bigger, but it's easier to see. Now we can go ahead and take p squared and end up rewriting it in terms of these Euclid's formula for it again. And we get this. Now, what is to notice is that R and S are coprime. That's because with Euclid's formula before, we noted that neither N and M shared any factors. So R and S share no factors, and therefore P shares no factors with them before, which is what we proved with the whole right-hand side of the equation thing. So keeping that in mind, let's go ahead and rewrite a squared by substituting in q. So now we can simplify that, and let's divide. So now we get a equals 2 square root of PRS. So what we know is that a must be an integer, which means that the square root of PRS has to be an integer. And P, R, and S share no factors. So what we can see from that is that the square root of P has to be an integer, the square root of R has to be an integer, and the square root of S has to be an integer, since they can't combine to multiply factors in order to get squares that can escape the square root. So that means that there must be integers j, u, and I, which when squared equal s, p, and r. So let's go ahead and define those. Let's just take these and rewrite it up here a lot bigger. So now that we have all these up here bigger, we can go ahead and plug everything in to p equals r squared plus s squared, which then goes and gives us u squared equals I to the 4 plus j to the 4. So what you'll notice is that this looks awfully similar to this. A to the 4 plus b to the 4 equals w squared. So let's remember all these previous formulas from before, which we said were true. Now we know that a is less than w from this top one. We also know that p is less than a from this middle one. You can clearly see that if these are integers, a is less than w, because b is also summed up in it. You can see that p is less than a, since it's part of this big square root of it times this r and times this whole big S. And you can clearly see that u is less than p, since u has to be squared to equal p. So what this all means is that u has to be less than w. But what you'll go ahead and notice is that it doesn't make any sense. Since we said w was the small solution, we said that w was the minimum. So this is completely contradictory. Here's my works cited, and here's my picture citations. Its contradictoriness means that there is no solution